Now that we have a basic understanding of how membrane potential is accomplished and maintained, let's look at the action potential. Obviously, we would see the action potential passing along the entire action of a neuron all the way. But in this example, we are just looking at a single spot along the axon over time. We will come back to connect this to the scale of a full nerve cell at the end. So there would be constantly a lot going on at the surface of a nerve cell's membrane wall. Think of what we learned about establishing neurons' membrane potential. However, here, for the sake of simplicity, I want to draw our attention to two specific channels that are the main driving force behind what we see. These are voltage-gated channels. So what this means is that they respond to an electrical charge close by this spot of an axon and then cause a change locally here too. Let's look at the sodium voltage-gated channel. Its structure has this little polypeptide ball on the bottom, so when the voltage approaches negative 55 millivolts, it will open. And it opens up wide, which allows a huge amount of sodium to come into the cell. We see this rush of sodium inside. Eventually, when we go away from that voltage, it's going to be inactivated, and then eventually it will close. So, once we hit the threshold of negative 55 millivolts in an action potential, all these voltage-gated sodium ion channels are going to open wide. As a result, there was this rush of sodium into the cell. As a result, it's going to depolarize the voltage of the neuron at that spot. So the voltage increases as we have this influx of sodium into the cell. There are also potassium-gated channels, and these are going to open wide when the voltage becomes around positive 30 millivolts. With this voltage, they will open wide, and they will only allow the movement of potassium outside from the cell. Okay, going back to an action potential. So here we had reached the positive 30 millivolts. Now, the potassium channels are wide open, and we have this rush of potassium out from the neuron. This causes the charge inside the neurons, this part, to drop. So we have repolarization. Sometimes it takes a while for these potassium voltage-gated channels to close, so it is common that we have an undershoot, so that the charge goes even below that of negative 70 millivolts. At this point, the voltage has gotten really low, and we need to give the normal membrane potential establishing processes to take place to create that normal resting potential of negative 70 millivolts. And only once this has been done, another action potential can take place. So far, we have been only looking at the changes in the charges of one particular spot of an action over time. What's really going on is that we have depolarization of a segment of neuron locally, which then triggers this change in the next segment, which at the same time, the initial segment recovers to change back to normal. As a result, we have an axon potential propagating along the neuron's axon.